Every time you flip a switch, a power plant somewhere must instantly respond. The grid is the world's largest machine, and it must balance supply and demand every single second. When you turn on a kettle, a generator somewhere spins a tiny bit faster. Millions of these tiny adjustments happen across a continent, all coordinated in real time. This system has kept our lights on for over a century. Today, we decode how the grid balances itself and why it's getting harder. It starts with generation. Power plants convert energy into electricity. Inside a steam turbine, superheated steam spins a massive rotor at 3,000 revolutions per minute. Wind farms harness the kinetic energy of moving air, turning giant blades. Solar farms silently convert photons into direct current electricity. Hydroelectric dams use the weight of falling water to spin turbines. The grid blends all these sources together, creating a single, synchronized supply. From the plant, electricity steps up to high voltage for long-distance travel. Transformers boost the voltage to hundreds of thousands of volts, reducing energy loss. Transmission towers carry three-phase power across entire countries. Major corridors connect generation hubs to cities, like arteries of energy. At substations, the voltage is stepped down, and power is routed to different regions. The transmission network is the backbone that makes the grid a true network. The brain of the grid is the control room, a 24/7 operation center. Operators monitor frequency, demand, and generation in real time. Grid frequency is the heartbeat, 50 Hz in Europe, 60 Hz in North America. If demand exceeds supply, the frequency drops. If supply exceeds demand, it rises. The control room's job is to keep that frequency exactly on target. They use forecasts of weather, TV schedules, and even sporting events to predict demand. Demand follows a daily curve, low at night, a morning ramp, a peak in the evening. To meet peaks, fast response gas turbines can start in minutes. Pumped storage hydro acts like a giant battery, storing energy for peak times. Electric vehicles can even feed power back to the grid when needed. Large industrial users can temporarily reduce their load in a demand response program. The result, a perfectly balanced grid, frequency held steady at 50 Hz. Renewables are clean but variable. The wind doesn't always blow, and the sun doesn't always shine. A cloud passing over a solar farm can cause a sudden drop in output. Grid-scale batteries now absorb excess renewable energy and release it when the wind drops. Hydrogen electrolyzers can turn surplus electricity into storable gas. Accurate weather forecasting helps grid operators predict renewable output hours ahead. The future grid is a smart network where every device communicates and balances itself. After transmission, power enters the distribution network, the final leg to your home. Voltage is stepped down again, first to 11,000 volts, then to 230 volts. Overhead lines or underground cables carry this low-voltage power into every street. Underground cables in cities are protected from weather but harder to repair. A smart meter on your home records your consumption and sends it to the utility. The circuit breaker panel is the final gateway before power reaches your appliance. The grid is a masterpiece of real-time engineering, balancing supply and demand every single second. It's one of the most complex machines humanity has ever built. Source Code Daily is where we bring these hidden systems to light. If you value understanding how the invisible world works. Thanks for watching. Keep decoding the source code behind modern life.